here, and current is sent through the coil. So when current, here a rheostat is also provided, and we can vary current in it. So when a varying current is sent through the coil, flux is directly proportional to that current. Yeah, phi is proportional to I, or phi equal to L into I. What is L? L is the constant of proportionality, that is the coefficient of self-induction or self-inductance of the coil. So here when a varying current is sent through the coil, what happens? An EMF will be induced in the coil, and that will oppose that current. See, first when we switch on the circuit, current begins to flow, and in a coil, that for the growth of current, for example 0 to maximum value I, suppose I is the current, and so 0 to maximum value, to reach that value from 0 to maximum value, it will take some time because we are sending it through a coil. Coil always opposes by inducing an EMF in itself. Because of that growth of current is get delayed. Similarly, when we switch off the current, that process also will produce a change in flux, decrease in flux, and that decrease in flux is also opposed by this coil. How the coil opposes the decrease in flux? By inducing an EMF in itself. Decrease in flux, how it can oppose? It has to send the current in the same direction of cell current. Then only decrease in flux can be opposed. So during the decay of current, the back EMF, that means EMF induced in the coil, that will support the cell current, that will same direction of cell current. During the growth of current, what happened? During the growth of current, that means switch on, when we switch on the circuit, current is increasing from 0 to maximum value. So that is known as the growth of current. Growth of current is varying, therefore flux linked with that also varies, and due to as the flux is varying, EMF will be induced in that coil due to that property of self-induction. So self-inductance is the property of the coil to oppose any change in the strength of current flowing through it. Any change, it may be growth or decay. So the coil has that property to oppose any change in the strength of current flowing through it. So how it opposes? By inducing an EMF in itself. So at the time of growth of current, the EMF induced will oppose that. You can see here in this figure, the cell current is from the left end to the right end. And during the growth of current, that induced EMF direction will be opposite to that. That means right to left, current will flow. And during the decay of current, what happens? Current is decreasing. Current is decreasing from maximum to minimum. At that time, induced current direction will support the cell current. That means left to right itself, the current will flow. Left to right itself. That will support the cell current. That means that is opposing the decrease of flux. So in effect, what we can see, combining both these facts, what we can say, coil opposes. Yes.
Can you please add Sri Lakshmi?
Okay. Sri Lakshmi, that's Shivagan. So what is self-inductance? Self-inductance is the property of a coil, by virtue of which it opposes the growth or decay of current. How? By inducing an EMF in itself. So that property of the coil, that is why the process of growth of current is delayed. Similarly, decay of current also is get delayed due to that property of the coil. Self-inductor, back EMF is induced. Due to that both the process, growth of current and decay of current, both are delayed. So self-induction is actually known as inertia of electricity. What is inertia? Inertia is the property of the body by virtue of which it opposes any change in the state of rest or state of uniform motion. Similarly, this coil is having the inertia of electricity. Electricity, that means current, inertia of electricity. So, it always opposes the change in current, That means always like to maintain a constant magnetic flux in that. Always like to maintain a constant magnetic flux in that. The current changes, flux changes. It doesn't like that. So, the magnetic flux linked with the coil is directly proportional to current through it. Flux is directly proportional to I. When more current is sent, more flux will be linked with the coil, more EMF will be induced because of the self-induction. Okay. So, flux is directly proportional to current. Phi equal to constant L into I, where L is known as self-inductance or coefficient of self-induction. Therefore, L you can write phi by I is a constant known as self-inductance. And you can define self-inductance here using this formula. We can define when I equal to 1, when we send 1 ampere current in that, what is the flux linked with that? That will give the self-inductance. So, when phi equal to Li, if I equal to 1 ampere, then phi equal to L. That is, self-inductance is defined as the magnetic flux linked with the circuit when unit current flows through it. So, how will you define self-inductance? Self-inductance is the magnetic flux linked with the circuit when unit current passes through the coil. Then one more definition is there for self-inductance. You see, induced EMF. When flux changes, EMF is induced. EMF induced E equal to minus d phi by dt. And phi, we know phi equal to Li. So, you can substitute in the place of phi, you can substitute Li. So, EMF induced E equal to minus of L into di by dt. L is constant for that coil, L is taken outside, L into di by dt. So, here also you can define self-inductance when di by dt is 1 ampere per second, current per time. When rate of change of current is 1 ampere per second, EMF induced will also equal to the self-inductance, or self-inductance is also equal to the EMF induced when the current changes in the coil at the rate of 1 ampere per second. So, that is another definition for self-inductance. So, two definitions we have studied now. Next, unit of self-inductance, Weber per ampere. Unit of self-inductance is Weber phi by I, Weber per ampere, or it is also named after the scientist who invented that, that is Henry, capital letter H. It is the unit of self-inductance, Henry, or you can use Weber per ampere. This is also a SI system. We have induced EMF E equal to L in magnitude, L into di by dt numerically. If di by dt is 1 ampere second and E equal to 1 volt, then L equal to 1 Henry. This is the definition for 1 Henry. Self-inductance of a coil is 1 Henry if 1 volt is induced in it when the rate of change of current in the coil is 1 ampere per second. So, definition of 1 Henry. What is meant by 1 Henry? Coil has self-inductance of 1 Henry. What is the meaning? When current change at the rate of 1 ampere per second induce an EMF of 1 volt in that coil, then self-inductance is said to be 1 Henry. So, how will you define? Current change at the rate of 1 ampere per second in the coil induces an EMF of 1 volt in it, then we can say the self-inductance of the coil is 1 Henry. That is the definition of 1 Henry. Next, self-inductance, very important derivation, self-inductance of a long solenoid. We have to derive expression for self-inductance of a solenoid. This is an important one. You can consider a coil here. Current is, I is the current sent through the coil, L is the length of the coil, A is the area cross-section of the coil. Then, so it is a solenoid now. What is the magnetic field inside the solenoid? B equal to mu 0 Ni. We have already studied this. Fatima is with. Now it is 38. Okay, very good. So here you see, you can see a solenoid here. Solenoid means actually a number of turns of insulated copper wire wounded in the form of a helix. That is a solenoid. So here, I is the current sent through the solenoid, and we already studied the magnetic field inside the solenoid is mu 0 and at the center part. At the end it is half mu 0 and I by 2, but we know at the center of the solenoid B equal to magnetic field induction B equal to mu 0 n I, where n is number of turns per unit length. Okay. Then flux you can calculate. Flux equal to BA cos theta, and theta is when theta is 0 here. Theta means what? BA angle between B and A. B magnetic field. Magnetic field is in this direction, and area vector is also in the same direction. So it's 0. Theta will be 0. So we can write flux equal to B into A. Total flux linked with this is flux linked with one turn. Therefore, total flux linked with n turns will be BAN, n turn. Total flux linked with n turn, BAN. But we know flux is also equal to L into I. When I is the current sent through a coil, then flux is also equal to Li, that we have studied. So we can equate both of these. Flux linked with n turn, BAN, flux equal to Li also. So we can equate them. Li equal to BAN. I get cancelled and we get L equal to mu 0 small n capital N and into A. And we know small n is capital N by L. No, that means number of turns per unit length. So we can substitute that. So mu 0 into capital N by L into N into A. So we get self-inductance of the solenoid equal to mu 0 N square A by L. Mu 0 N square A by L, where N is total number of turns in the solenoid. A is area cross section of the solenoid. L is length of the solenoid. Mu 0 permeability of free space. If the coil is wound over a material having relative permeability mu r. So in the coil, if they see here it is vacuum. Instead of that, if the coil is wounded over an iron piece or any other material, if the coil is wounded over an iron piece or any other such material, iron piece, permeability is more. So flux linked with that also will be more. So that magnetic field, more magnetic field will be produced. If we wind all this wire on a soft iron core, like that, more magnetic field, we get more magnetized, strong magnet we get. So if the coil is wound over a material having relative permeability mu r, so air is having permeability mu 0, instead of that, if we keep another material like a soft iron which is having a permeability mu r, then we know mu r equal to mu 0 equal to mu. In another material, instead of mu 0, what we have to write? Mu. And mu equal to mu 0 into mu r. Mu equal to mu 0 into mu r. So mu by mu 0 is mu r. So mu in the place of mu, what we have to write? Mu 0 into mu r. So this is for another, when a wire is wounded over another material of relative permeability mu r. Permeability of different material will be different. So self-inductance of a solenoid expression, very important. All of you have to write and study. Remember always the final expression, by heart it. Mu 0 n square A by L. Okay. Next, and it depends on what factor, self-inductance. From the equation you can tell mu 0 n square A by L. So directly proportional to what all factors? Number of turns, area cross section, and relative permeability divided by L. So it is inversely proportional to length. Okay. Factors on which self-inductance of a coil depends: number of turns, capital N, area cross-section, capital A, permeability of the core of the material. The next, mutual induction, another. So self-induction we have studied. Next is mutual induction. Mutual induction, you have to consider two coils. For example, one primary coil and other secondary coil. Two coils you have to consider. And in one coil we send current. We send current through one coil. You see, primary coil, you can name it primary coil, and this is secondary coil. And we send current through the primary coil. So you can see a key also, tapping key. Just when we press the key, current flows through that from 0 to maximum value. We are telling 0 to maximum because current is sent through the coil. It will take some time to reach from 0 to maximum value due to back EMF induced in the coil. Back EMF will be induced in the coil. So first when we switch on the current, what happens? Flux linked with that changes because current is a varying current. 0 to maximum value, current is varied. So flux linked with that changes. Whenever there is a change in magnetic flux, and EMF will be induced in the neighboring coil also. Same coil back EMF induces, that we have studied, self-induction. And now we are dealing with mutual induction. So if we keep another coil near to it, and you just connect a galvanometer to it, whether current is induced or not, that we can detect if you connect a galvanometer in the secondary coil. Just connect a galvanometer in the secondary coil. So two coils are there. One is primary coil, other is secondary coil. Primary coil we connect a battery and a tap key. And secondary coil we connect only a galvanometer. And now what is done? When we switch on the circuit, current passes from 0 to maximum, varying current. Why varying? Why it is varied? Because of the back EMF. It takes some time to reach from 0 to value to maximum value. So here when we switch on the current is changing. Changing current will produce a changing magnetic field, and changing magnetic field induce an EMF in the neighboring coil. See, flux lines, that red line shows the magnetic flux. So when current is varied, flux linked with that varied, and that flux is linked with the secondary coil. So an EMF will be induced in it to oppose that growth of current in the neighboring coil. You see, here the current, direct cell current is towards right, positive, positive to negative current flow, left to right current flow. So the flux here, clockwise direction current, and current is passing in the clockwise direction. That is how you get positive clockwise. You have to look the positive terminal of the battery. You see, current is flowing like this. Clockwise. ക്ലോക്ക്വൈസിലാണ് പോണത്. നമ്മൾ വൈൻഡിങ് ഇങ്ങനെയാണെങ്കിലോ, ഇങ്ങനെയാണെങ്കിൽ ആൻറ്റി ക്ലോക്ക് വൈസ് ആവും. അപ്പോൾ വയർ വൈൻഡ് ചെയ്തിരിക്കുന്നത് ഇങ്ങനെയാണ്, കണ്ട ക്ലോക്ക് വൈസിലാണ് കറണ്ട് ഫ്ലോ ചെയ്യുക. അപ്പോൾ ഹിയർ ദ സൗത്ത് പോൾ വിൽ ബി ഡെവലപ്ഡ്, and this end north pole will be north pole. So it becomes a magnet. The magnetic field lines outside north to south. I have drawn only two field lines, but we have already drawn in while studying solenoid. Large number of field lines we have drawn around the solenoid. Here only two field lines are drawn. Okay? And that field line is linked with the secondary coil. If it is kept in this manner, maximum flux linkage. If it is kept one over the other, the linkage will be maximum. But even though you are not keeping it one over the other, it magnetic flux also link with the secondary coil. If it is kept in this manner also, flux lines and field lines are linked with the secondary coil also. So whenever there is a change in magnetic flux linked in the first coil, due to the change in current, that flux will be linked with the secondary coil also, and an EMF will be induced to oppose the cell current. To oppose the cell current, an EMF will be induced. So here in this end it becomes opposite pole. It will be developed, not like that. It will be developed to oppose that. To oppose that, north pole will be developed. So current will flow the opposite direction. So induced current flow in this direction, left to right, induced current. And during the make of the circuit, that means growth of current. and during the break of the circuit, it will support the base current, support the cell current during the break of the circuit. Break means decay of the circuit. When we switch off, the current get decayed, and at that time decrease in flux is produced, and that is to be opposed. How? By inducing an EMF in the secondary coil, and it will send current to support the cell current. During the decay of current, the current induced will support the cell current. Okay. So that property of the coil is known as mutual induction. So how will you define mutual induction? It is the property of two coils. So when we discuss about mutual induction, two coils are to be mentioned. It is the property of two coils by virtue of which each opposes any change in the strength of current flowing through the other by developing an induced EMF. So each coil, so when current in this changes, this coil opposes it. Understand? So it is the property of the two coil by virtue of which each opposes any change in the strength of current flowing through the other by developing an induced EMF in it. So that is mutual induction. It is the property of two coils by virtue of which each opposes any change in the strength of current flowing through the other by developing an induced EMF. So flux here also, the flux change is directly proportional to current, or phi equal to MI. This is mutual induction. So M we use, self-induction we use L. So mutual induction phi equal to MI, therefore M equal to phi by I. When I equal to 1 ampere, phi equal to M. So we can define mutual inductance. So mutual inductance between two coils is defined as the magnetic flux linked with the neighboring coil when current is 1 ampere current is sent through it. When 1 ampere current is sent through it, whatever flux is linked with the neighboring coil, that is mutual inductance. Mutual inductance is the flux linked with the neighboring coil when current changes. Current in the neighboring other coil is 1 ampere. Current in this coil is 1 ampere. Whatever flux is linked with the secondary coil, that is the mutual inductance. Okay. Here, another definition for mutual inductance, we know phi equal to MI, therefore EMF induced E equal to minus d phi by dt, and substitute for phi equal to MI, you can substitute here, M is constant, you can take it outside, E equal to minus of M into di by dt. When di by dt is 1 ampere per second, E will be equal to M numerically E will be M. So EMF induced in the coil is equal to the mutual inductance when current changes at the rate of 1 ampere per second in the other coil. When current changes at the rate of 1 ampere per second in the other coil, EMF induced in the neighboring coil is equal to mutual inductance. So E equal to M, mutual inductance between two coils is numerically equal to the induced EMF in one of the coil when the rate of change of current in the other coil is unity. As a unit of mutual inductance is Weber per ampere, same as self-inductance. It is Henry, named after the scientist, and denoted with the letter capital letter H. Then here also we have to derive the expression for mutual inductance of two long solenoids. Mutual inductance. Self-inductance we have derived E0 n square A by L. Here you can see what is the expression for mutual inductance of two long solenoids. So for that you have to consider two coils. Show the figure. You can see the figure. See, primary coil, you can see that brown colored pan is drawn, primary coil, and a blue colored pan is drawn, secondary coil. It is wound one over the other. Area cross section here we consider as same. So different cases are possible, but here we consider it is one over the other, it is wounded. So area cross section is same. In that way we have considered. And suppose A is the area cross section common for both. And N1 is the number of turns in the primary, and N2 is the number of turns in the secondary. And flux, when I current is sent through the primary coil, flux linked with the secondary phi equal to flux equal to BA cos theta. If there are N2 number of turns, N2 into BA. And here cos theta is 0, magnetic field inside the solenoid, and area vector, both are in the same direction. So we can take 0. So BA cos 0 is 1. So BA. And flux linked with the secondary we are finding. So its number of turns we have to write here, BA into N2. Current is sent in the primary coil. We are calculating the flux linked with the neighboring coil or secondary coil. So its number of turns we have to write here, BA_N2. B equal to mu 0 Ni. Phi is the current sent through the solenoid. What is the magnetic field inside at the center part? The center part mu 0 Ni. What is N? Number of turns per unit length. So mu 0 Ni A into N2. That is the flux linked with the secondary coil. But phi equal to Mi, we know. So we can equate them. For Mi equal to mu 0 Ni A N2. I get cancelled and we get M, mutual inductance M equal to mu 0 small n N2 into A. And small n is the number of turns per unit length. So we are writing N1 by L. N1 is the number of turns in the primary coil. So N1 by L, that is small n. So substituting that, we get the expression M equal to mu 0 N1 N2 A by L, where A is the area cross section. That is, we have taken it same. And then some other case is there. If area cross section is different, we have to take area cross section of the shorter area cross section we have to consider, because that much area only the flux will be linked. That is a special case. When area cross section is different, we have to consider area cross section of the shorter one. If mu r is the relative permeability of the core, the mutual inductance M equal to, in the place of mu r, mu comes and mu equal to mu 0 into mu r, that is substituted. For mutual inductance M equal to mu 0 mu r N1 N2 A by L. Other case, self-inductance, it is self-inductance L equal to mu 0 mu r N square we have taken. Here it is N1 number of turns in the primary, N2 number of turns in the secondary into A by L. So it is easy to remember. There it is N square, here it is N1 into N2. And the factors on which the mutual inductance depends. Number of turns, from this equation you can tell factors on which mutual inductance depends. N1 number of turns in the primary, N2 number of turns in the secondary, area, capital A is the area of the coil, and the relative separation also it depends. Then relative orientation of the two coil, that means whether it is kept one over the other or whether they are kept perpendicular to each other, like that. Relative orientation, it depends on relative orientation of the two coil, and also permeability of core material, depends on permeability of the core material, that is this mu r, relative permeability. So self-inductance and mutual inductance we have studied. In that we have to derive the expression for self-inductance of a solenoid and mutual inductance of a solenoid. So phi is proportional to what? Flux linked with the coil is directly proportional to what? Who will tell that? Flux linked with the coil is directly proportional to current. Flux is equal to Li in the case of self-inductance, and flux is equal to Mi in the case of mutual inductance. Then next, last part of that chapter, electromagnetic induction. Not last, energy stored in the inductor. Okay. So here you can see an inductor. That means a coil with inductance L. L is the inductance of the coil. I is the current sent through the coil. Then you know a back EMF will be produced in the coil. When we send current through the coil, back EMF, opposing EMF will be induced in the coil to oppose the growth of current. And suppose L is the self-inductance of the coil. Then EMF induced in the coil equal to minus of L into di by dt. Phi equal to Li, E equal to minus d phi by dt. From that, E equal to minus of L into di by dt. That is the equation. Minus of L into di by dt. Then the work done against the back EMF in a short time dt is equal to, see here we use the equation dw by dt power, dw by dt, that is the work done per time, that is E into I, V into I power, E into I power. So dw equal to EI into dt. We start with this equation. Work done. What we are calculating? Energy stored in an inductor. When I current is sent through the inductor, what is the energy stored in it? L is the self-inductance of the coil. Energy stored expression. So we find the work done to send current through the coil. Why we are doing work to send the current? Because of the back EMF. So when we begin to send current through the coil, a back EMF will be induced in the coil. Against that back EMF, the battery has to do work to send current through the coil. So work done against the back EMF in a small time dt is dw equal to EI dt. So which equation we start? Power equation. Power equal to EI. Power is work done by time. So work done equal to EI dt. From that equation we begin. So what is EMF induced? Opposite to that, we have to, battery has to do work. In order to send current, we have to, our battery has to do work. What is the back EMF? Minus of L into di by dt. So battery has to do a work opposite to that. So minus of minus L di by dt, that is to be applied. Applied EMF must be opposite to this back EMF. So we put positive sign here. E equal to induced EMF is this. So opposing EMF, applied EMF must be equal and opposite to that. So plus L into di by dt. Here you can see work done against the back EMF. This is back EMF, and work done against the back EMF equal to minus of this value. So EMF you have to take minus of this value. L into di by dt into I dt. And here dt dt cancel, and we get Li di. Therefore, total work done when the current grows from 0 to I, that we have to integrate the expression from 0 to I, Li di. L is constant, self-inductance, it is taken outside, and I di, integrating I di, what we get? I square by 2. I raised to 1 it is. I raised to 1 plus 1 by 1 plus 1, that is equal to I square by 2. So, half Li square, W equal to half Li square. Work done is equal to half Li square. This work done is stored in the inductor as the magnetic field energy. So work done, what we got? Half Li square. That is the expression for energy stored in an inductor. Okay. Energy stored, how we calculate? From this equation. E equal to EI dt, the work done equal to EI dt. 5 minutes more. So work done we calculated W equal to half Li square. What is L? Self-inductance. What is I? I is the current sent through the inductor.